Okay, so we have started discussion on experimental planning in the previous lecture, and in terms of experimental planning, we were starting with an example, and we saw that the example is for determination of a forced convection heat transfer coefficient of a new refrigerant. So these were the conditions which were listed over here, and based on these conditions and whatever prescribed over here, what we have done, actually we have tried to plan the layout, physical layout of the experimental facility. Okay, and in this physical layout, if we try to see, some of the major equipment were a tube which will be having sufficient length in order to have developed flow regime, because we have to estimate the heat transfer coefficient particularly in the fully developed flow regime. So in this tube, initially we will be considering the length such that the flow can fully develop, and after that whatever the portion is there we will try to provide heating. And for heating the tube, we were using some variable power supply heaters, because if we have to vary the heat supply over or heat flux over a wide range, then we should be able to supply that power from the input heat source. And once the refrigerant which is flowing inside and coming out of the heated section, its temperature will be more. But ultimately, if we have to repeat this experiment for longer duration, so what we need to do, we need to obtain the refrigerant in the tank or accumulator at the initial condition. To do so, what we have done, we have actually installed one heat exchanger over here. So if my refrigerant is staying in the single phase regime, then this particular heat exchanger will be cooling this temperature from T out to again the supply temperature T in. And after this, we have a pump which will be actually pumping the pumping the refrigerant into the supply line. And in order to measure the flow rate of the refrigerant, we have to use the flow meter. Okay, and some of the measurements we need to do are important ones are the measurement of temperature. Of course, along with the measurement of temperature, we may have to do the measurement of pressure as well. So for recording temperature, one temperature sensor we will be inserting within the tube, so that it can give the temperature of the refrigerant when it is entering the tube, and one will be giving the temperature when it is actually coming out of the tube. And other than that, we know that because over here we are trying to determine the forced convection experiment. So what we need to do, we need to apply over here Newton's law of cooling. So as per Newton's law of cooling, for this type of configuration, the heat flux is given in terms of H times T wall minus T fluid. Okay, so ultimately T fluid we are trying to measure with the help of these inner and outer thermocouples. So ultimately we have to also measure the wall temperature. Okay, so to measure the wall temperature, we need to insert thermocouples at multiple locations. However, what should be the appropriate distance between the thermocouple locations, that we need to decide based on the our desired outcomes as well as the physical system. Okay, so this physical layout is clear to all. Now let us try to see one by one what are the steps listed over here. So this is again the simple arrangement of uh, the schematic representation of the physical layout is shown. So here you can see this is shown in terms of water, but over here our interest is to determine heat transfer coefficient for the refrigerant. So this refrigerant we will be going, and then this is T1 and T2 are the inlet and outlet temperatures, and then you can see these thermocouples over here are representing the wall temperature. Okay, and ultimately this particular tube is subjected to some potential. So this test section is actually heated over here, and we are using some variable supply over here. And other than that, you can see that whatever the heat we are supplying to wall of the tube, that heat should not escape out to the environment. Okay, so ultimately all the heat whatever we are supplying over here that entire heat should enter into the refrigerant, because whenever we are calculating heat flux, so this heat flux we will be calculating by the formula V into I divided by area of the tube. Okay, so once we are considering the V into I, that is the heat which we are supplying. So if we are equating this to H into TW minus TF, in that scenario this entire heat must go to fluid medium. Okay, so that's why what we need to do, we need to provide certain insulation also over here. Is this one clear? Okay, so let us first try to theoretically estimate the heat transfer coefficient. So it is given in the question that Reynolds number has to be varied from 20,000 to 1,50,000, and ultimately the diameter of the tube which we are considering, that will be varying from 2 to 35 mm. So these are the conditions which are given in the question. So first thing what we will do, we will try to estimate that how much theoretically would be the heat transfer coefficient. Okay, so this range of Reynolds number 20,000 to 1,50,000, and whenever our diameter is from 2 to 35 mm, then can you tell me, so if diameter is 2 to 35 mm, it means our tube is of circular cross section. So we are talking about a circular tube, and ultimately Reynolds number is greater than 20,000. So this is the situation of nothing but the turbulent flow. Okay, and it is also given in the physical scenario that we have to perform the experiment for fully developed flow conditions. So ultimately it means whenever we have to estimate the heat transfer coefficient, our situation will be fully developed turbulent flow. Is this point clear? So situation will be fully developed turbulent flow. Now theoretically, if I have to estimate heat transfer coefficient for fully developed flow, what is my relation? There are various heat transfer coefficient relations available if you study your convective heat transfer in your basic heat transfer course. So one of the very important relation which typically used in estimation of heat transfer coefficient for fully developed turbulent flows, that equation is known as Ditus-Boelter equation. And as per Ditus-Boelter equation, Nusselt number is equal to 0.023 into Reynolds number power 0.8 and Prandtl number power n. Okay, where n is equal to 0.4 if heating of the working fluid is taking place. Okay, like the scenario we are having where tube wall will be hotter and refrigerant fluid will be colder. So it means refrigerant will be gaining the heat from the wall. So its heating is taking place. In the scenarios where hot fluid is moving through the wall, moving through the pipe, in that case what will be happening? If pipe wall temperature is low, then the working fluid will lose the heat and cooling of the working fluid will be taking place. So for cooling, this coefficient n is considered equal to 0.3. Is this point clear? So this Ditus-Boelter equation is a very famous equation, and for majority of the industrial design of heat exchanger and forced convection systems, particularly in the turbulent flow design, this equation is actually popularly used. Okay, so because this is a popular equation which fits almost majority of the configurations and the wide range of working fluid for determining heat transfer coefficients. Okay, so what we will be doing now, whenever my Reynolds number is 20,000 and D is equal to 35 mm. Now Nusselt number, how I can write? Nusselt number can be written in terms of HD by K, where K will be my thermal conductivity of the refrigerant, and so I can calculate H from here. So what was the Nusselt number? Nusselt number is 0.023 into Reynolds number power 0.8 into Prandtl number power 0.4. So Prandtl number is given in the properties as 5.6. So 5.6 power 0.4. Now this entire up to this, it is my Nusselt number. In order to calculate H, this Nusselt number must be multiplied with thermal conductivity of the refrigerant, which is 0.075, and divided by diameter. So ultimately my heat transfer coefficient theoretically which I should get for 20,000 Reynolds number at 35 mm diameter is 271 watt per meter square degree Celsius. Okay. Likewise, I have estimated for it for smallest diameter pipe also, and for smallest diameter pipe it comes out to be 4740 watt per meter square degree Celsius. Okay. And for 1,50,000 Reynolds number with smallest diameter pipe, it comes out to be 23,760 and 1,360 for 35 mm diameter. So you can see the expected range of heat transfer coefficient is from 271 to 23,760 watt per meter square degree Celsius. Okay. So from here we can see this is the expected range of heat transfer coefficient. Is this one clear? Now what we need to do? Whenever we are using this physical setup, in this physical setup we have seen that we are having one flow meter. So ultimately to determine the range of flow meter, or to select a particular flow meter, what we need to do, we need to determine the mass flow rates or say volumetric flow rates associated with these conditions. Okay. So to do so, for Reynolds number of 20,000 and diameter of 2 mm, if I calculate area and then if I try to estimate the mass flow rate, it comes out to be 9.42 into 10 square kg per second. Is this one clear? For 35 mm, it comes out to be 2.89 kg per second. Now, if I consider the Reynolds number of 1,50,000, then this number comes out to be 0.071 kg per second for 2 mm pipe, and for 35 mm pipe, it is 21.6 kgs per second. Okay. Now, it is interesting to note that what is the smallest flow rate obtained? 0.071 kg per second. And what is the highest flow rate obtained? 942 kg per second. Okay. So it means that in your experimental system, if you have to test all the pipe diameters, then the range of flow rate which you are getting, that is excessively high. If you see, the order of this quantity is close to 10 to power minus 2, and order of this quantity is close to 10 to power 3. Okay. So it means that you need a flow meter which can measure the mass flow rate in this wide range. Okay. So obtaining this type of flow meter will be actually extremely challenging, because what happens typically, if you take a device with that much wide range, then sensitivity of that particular device will be actually low, and particularly whenever in the low mass flow rate region, whatever the reading it will be giving, that will not be accurate enough. Okay, so it means that if I have to do testing with all the pipes of 2 mm and 35 mm as well, diameter as well, then I will not be able to perform this with the help of a single flow meter. At least 2 flow meter I require, one which is having good precision for smaller flow rate measurement, and one which can operate at the high range of flow rates. Okay. So to avoid this type of complicated situation, because you cannot use, say, ultimately it will be putting some burden in terms of cost. Okay. So first what we will do, we will try to select over here certain diameter, a single diameter of the pipe. Of course, so if you have to do measurement from 2 mm to 35 mm, again there will be issue that large number of pipe diameters you have to actually use for your measurement. Okay, so this process will be becoming again a cumbersome process. So what we will do, instead of at the initial state itself planning for large number of experiments with large number of diameters and multiple instruments, we will try to take some simplified approach where what we will do, we will take a single representative diameter of all these pipe diameters, and for that single representative pipe diameter, whatever the range of flow rate we are getting, we will try to select the flow meter for that particular range, and we will do initially experiment with the single diameter. And if that single diameter is either matching with the well established theory, then what we can do, we can simply use that theory for estimation of heat transfer coefficient in all other pipe diameters. Or if it is not matching with any established theory, then with the help of experimental data, whatever we will be obtaining for this single diameter pipe, with the help of that we can develop some heat transfer coefficient correlation, and that we can use for other pipe diameters. And of course, in that scenario, once we have proposed some correlation, in order to test that for other tube diameters, we may have to repeat experiment for one more tube diameter. Is this point clear? Because ultimately, if you try to consider the entire range, then there is no limit. You may have to take 2 mm, 2.5 mm, say 3 mm. So likewise, the number of diameters which you have to test will be becoming huge. Okay. So what we will be doing over here, because before selecting that single diameter, let us try to see the other parameters as well. Okay. So in terms of heat transfer rates, if you see, for 2 mm diameter pipe, this will be my surface area, and for 35 mm, this will be surface area. Now if we have to use the, if we have to calculate the value of H, so H already I have established, okay, in the first slide using Dietz-Boelter equation, and it is given in the question that maximum difference between wall temperature and fluid temperature should not exceed 15 degrees. Okay, so we have to estimate this in the range such that wall temperature minus fluid temperature is in the range of 15 degrees Celsius. Is this point clear? So for obtaining this, now we have to determine how much amount of heat we need to supply. All are clear with this point? So if my TW minus T fluid is 15, area is known for 2 mm pipe, heat transfer coefficient for 20,000 and 2 mm we have calculated using Dietz-Boelter equation. If I substitute all this, then I am getting required heat transfer rate of 896 watts. If I increase diameter to 35 mm and 20,000 Reynolds number only, then my required heat is 894 watts. Similarly, for 1,50,000, if I calculate, it comes out to be 4491 and 4488. So it means that after obtaining this, we have come to know that if we have to take power supply, that power supply should be able to supply power in the range of 894 to 4491 watts. Okay, is this point clear? Now, what is the next parameter? Next parameter is length. Okay, so over here, what they have done, it is assumed that the length of the tube is 2 meter. Okay, straight length of the tube is 2 meter. Now if you have to see how much will be the change in the fluid temperature, to calculate that, delta T fluid will be equal to, so this is done for Reynolds number of 20,000, diameter of tube of 2 mm and length of the tube of 2 meters. So if we do so, delta T fluid, it comes out to be power divided by, how we will be calculating, please tell me. Q will be equal to mass flow rate of the refrigerant into Cp into T out minus T in. So this is the delta T fluid. Okay, and Cp is given in the data. Okay, so once we use this information, we get that change in temperature of the fluid will be 67.9 degrees Celsius if we consider 20,000 Reynolds number and 2 mm diameter. However, if I consider 35 mm, then change in temperature will be only 0.22 degrees Celsius for same heat input, and for 1,50,000 it will be 45.2 and 0.14 degrees Celsius. Okay, so you can now see that till now we have not performed any experiment, but before performing the experiment itself, by using some known relations from the theory, we have actually estimated almost all the parameters that what will be their expected range. Why this it is desired to obtain this expected range? As I told you, it may not be true that the actual data will come exactly in these values, okay, but ultimately even if there is some deflection in the actual data, that will be actually close to these values. So ultimately, because if you do not have any information available before planning the experiment, then how you will be selecting the flow meter, okay, or how you will be selecting the temperature measurement device. So ultimately some approximations based on the known theories we have to do before starting the experiment, and based on that actually we can determine all our parameters. Okay, so previously I told you that whatever the ranges we are obtaining, particularly for mass flow rate. Yes.
Sir, how will we select a device for for experimental values? जैसे flow rate, flow meters and thermocouples जो भी हम use कर रहे हैं, वो theoretical values के लिए calculate कर रही है, but it may happen that experimental values उससे exceed कर रही है.
Yes.
So कितने ज़्यादा range के लिए वो device?
So whenever the experimental values will be exceeding, these may exceed by 25%, 30% or 50%. Okay, but it will not be exceeding by one order or two orders. Like the values will not be becoming 200 times or 500 times of the obtained value. Okay, so unless or until your variation in the data is well within the 100% limit, in that case we will be getting that almost all our readings will be coming in the same order as expected. Okay, but if you are considering that it is varying by say 500% or 1000%, then order of magnitude will be changing, and in that scenario actually again the selection of device will be actually changing. Okay, so normally of course there are the variations. So if say you are getting somewhere that your power is ranging from 894 watt to 4491 watt, of course you will not be getting any power supply which is precisely giving you these two numbers. You have to select a power supply somewhere from 500 watt to say 5000 watt, okay, which is a standard number. Or you may think that okay, you may have to go for slightly high heat flux, so instead of 5000 let us go for 8000 watt. Okay, so this much deviations or this much slightly larger range we can consider, but it should not happen that your calculated value is 4491 and your required value is coming 44910. So of course that is actually some absurd estimation. Okay, so that's why that type of deviations is not possible, but whatever the small possible fluctuations will be coming either because of the uncertainties and assumptions involved in the theoretical analysis, these type of variation can be accounted for by providing some small tolerances. Okay. Okay, so we discussed that whenever we were trying to estimate the mass flow rate for the tube range of 2 mm to 35 mm, then the variation of particular the requirement of flow rate range was excessively high. Okay, so as I told you, and again one more thing we discussed, that using the multiple tubes will be making the process as cumbersome, and it will be also cost consuming. Okay, so initially what we will do, we will take a representative tube. So out of the range of 2 mm to 35 mm, one representative tube size we are considering as 12 mm diameter, and this 12 mm diameter is again more suitable from the market availability point of view. Okay, so typically whatever this your home refrigerator, air conditioning units you will be seeing, there you will be finding your tube diameter majorly ranges from 8 mm to 12 or 15 mm. Okay, so that's why the availability of this tube will also be easy. So we have frozen the diameter as 12 mm. Of course, I am not saying that everyone has to freeze diameter as 12 mm. You may go to 15 mm, 20 mm depending upon the availability, but it has to be within this range, and try to take some mid value so that it covers almost the spectrum on lower end as well as on the higher end. Okay. And inlet temperature, we are considering that we will restrict our fluid to enter the tube at 0 degree Celsius. Okay, and then the average wall temperature minus fluid temperature is equal to 15 degrees Celsius. So these are the conditions which we want to maintain. So for these conditions, if I consider Reynolds number of 20,000 and Reynolds number of 1,50,000, these are the two extremes. We have to do measurements from 20,000 to 1,50,000. Okay. So in these two extremes, if you calculate the mass flow rate, it comes out to be 0.0566 kg per second and 0.424 kg per second. So again, only there is a difference of one order. So probably we will be easily able to get a device which can measure the flow rate in this range. Okay. Heat transfer coefficient, if you see, so that will be expected outcome will be from 790 to 3961. And the requirement of power will be from 894 to 4480. So all the calculations which earlier I have shown for 2 mm and 35 mm, now all these calculations are repeated for 12 mm. Okay. And T2 minus T1 is considered 11 point. So if you do calculation, then you will be finding that rise in temperature of the refrigerant will be 11.3 degrees Celsius for 20,000 Reynolds number and 7.55 degrees Celsius for 1,50,000 Reynolds number. Okay. Again, the point is we have earlier in all these analysis we have taken the tube length as 2 meter. So we have to check whenever we are considering this length as 2 meter. Particularly if we are considering 2 meter, it means 2 meter is my which section? Heated section. So before the heated section 2 meter, I have to provide some length of unheated section as well. Okay. So my length of the unheated section should be greater than the entrance length required for the turbulent flow. Okay. Because whenever we are coming to heated section, then flow should be in the fully developed state. Okay, now let's try to see the proposed measurement methods. So, if I have to measure T1 and T2, T1 is 0, and if maximum temperature is changing by 11.3 degrees Celsius, it means outlet temperature will be 11.3 degrees Celsius. So, I can choose type E thermocouple which measures the temperature in the range of 0 to 40 degrees Celsius. Now this question is answered. So you have actual requirement of 11.17 degrees Celsius, but we are taking the range up to 40 degrees Celsius. So of course 11 to 40 is a huge margin. If it is going beyond 40, then it means there is some issue with the initial theoretical analysis. Okay, and the estimated uncertainty of this type of measurement is plus minus 0.5 degrees Celsius. Okay, and another arrangement which can be used for measurement of the temperature difference. So thermocouple is something which measures the temperature at a particular location, but we do have another alternative which is called as thermopile. So thermopile is a thermocouple arrangement which directly gives the differential temperature between two locations. Okay. So instead of using the type E thermocouple, I can also directly measure the difference T2 minus T1 by using a thermopile arrangement which will be having range of measurement in the limits of 0 to 15 degrees Celsius, and uncertainty will be plus minus 0.3 degrees Celsius. Okay. So if you use thermopile arrangement, then the uncertainty will be slightly lesser in comparison to when you are using the simple thermocouple. Is this point clear? And from where to select this thermocouple? So typically for different type of thermocouples, there is a standard table available where their operating range and estimated uncertainties are listed. For example, if your measurement is involving say temperature range in the limits of 25 to say 1000 degrees Celsius, then you may have to go to K type thermocouple, which measure temperature up to say 1500 degrees Celsius or so. Okay, so this depends upon our requirement. So immediately whenever I am selecting the devices, if I have to select temperature measurement device, I will be referring to the standard table for thermocouples. Okay. Now again, what I need to measure? I need to measure the wall temperature also. Okay, and in terms of wall temperature, we have created limit that average wall temperature minus fluid temperature should not exceed by 15 degrees Celsius. So in case my temperature of the outlet fluid is going up to 11 degrees Celsius, then ultimately at that location the wall temperature should be 15 degree larger than this. So which is coming out to be around 26 or 27 degrees Celsius. So we have to consider wall temperature again a device which can measure in the range of 40-50 degrees Celsius. Okay. So to do that, we have now again E-type thermocouple, and this thermocouple is actually measuring this will be required to measure the temperature in the range of 0 to 60 degrees Celsius and plus minus 0.5. Now we have to measure the mass flow rate. So for mass flow rate, again you will be finding different type of flow meters. Coriolis mass flow meter, turbine type mass flow meter, ultrasonic mass flow meter. Okay, so all different types of flow meters are available. Among all the flow meters, if you are operating, so each of the flow meter have their specific features. If you are operating in the two-phase regime where liquid and vapor are simultaneously forming, under that scenario we have to go for ultrasonic flow meters, okay, or electromagnetic flow meters. Sorry, not ultrasonic flow meters but electromagnetic flow meter. If I am operating in the purely single phase regime, then I can use either turbine flow meter or Coriolis mass flow meter. Typically the cost of Coriolis mass flow meter will be slightly high in comparison to the cost of a turbine flow meter. So for our measurements, we can, by having a good compromise in between the cost and required accuracy, we can choose turbine flow meter over here, and the range of this turbine flow meter is 0.05 to 0.5 kg per second. Okay, so again it is meeting our required range, and corresponding uncertainty is plus minus 0.5 degrees Celsius. Then voltmeter and ammeter. So of course we have to measure the for supplying the power of 894 to 4480 watt, my voltage and current will be changing in what range. Okay, so by doing so, voltmeter and ammeter are selected in the range of 2 to 20 volts and 100 to 400 amperes. Okay, now one important point you can observe over here. This this voltage range is in the range of 0 to 2 volts, which is a very small value, and current is in the range of 100 to 400 amps, which is a very large value. So why this type of arrangement is used? What is the reason? So typically what we are doing over here, we are using the electric power to heat our tube section. Okay, and we know that the amount of heat generated is given by Joule's heating law, which is I square RT. Okay, so the amount of heat generated is directly proportional to square of I. if I write it in terms of voltage, then 1I into R will be becoming V, so it will be becoming VIT. So if I see Q is directly proportional to V, but it is directly proportional to I square. So it means that if I give the large current, then amount of heat generated will be significantly high. So typically, whenever we use the power supply for heat transfer experiments for achieving the high heat flux rates, always the characteristic of the power supply should be such that its voltage rating should be small and current rating should be high. Okay. And of course, for pressure measurement, we are using Borden gauge. And if required, transducer can be used for continuously monitoring the pressure for longer duration. Is this one clear? So selection of instruments is clear to all. So based on the initial theoretical estimate, how we can actually select the particular instrument. Of course, in order to select these instruments, you should have the knowledge of the different type of instruments which are available in market. Okay. Okay, so now what we need to do? We need to do uncertainty analysis. So for doing uncertainty analysis, first I have done Reynolds number of 20,000, and here I am writing power using two ways. One is electric power. Okay. So what is the meaning of electric power? If I calculate Q is equal to V into I. And one is power using flow energy. What is the meaning of flow energy? If I calculate Q is equal to how? M dot Cp into T out minus T in. Okay. So if I calculate power using flow energy, then my uncertainty in measurement will be 0.027. If I measure power using this electric power formula, then uncertainty will be 0.004. Okay. So ultimately, what I am getting that electric power is actually, so the measurement using electric power using voltage and current is giving me least uncertainty, so I can utilize this method. Okay. So similarly, you can see for 1,50,000 as well. But one important point you have to note over here. If you have to estimate whether your experiment is working properly or not, how you can check? The checkpoint is, if you calculate Q is equal to V into I, that should be nearly equal to M dot Cp into T out minus T in. Is this point clear? If there is a large difference between this and this, what it means? It means your insulation is not sufficient enough, and significant amount of electric power, ultimately if it is not correct, then this will be always greater in comparison to this value. So in that scenario, you can easily estimate that your insulation is not proper and some amount of heat leakage is taking place, and what you need to do, you need to actually correct the insulation before performing the experiment. And if this side is coming greater, it means that some of the measurement device is actually not performing properly. All are clear with this point? Now, heating device design calculation. So ultimately, we have to also control the voltage and current in the heating device. So for heating device, of course, inside diameter is 12 mm. And if you refer to the tubes available in market, the wall thickness will be 0.8 mm. Of course, the wall thickness depends upon the requirement of the pressure. So if you have high pressure requirement, then wall thickness will be more. If you have low pressure measurements, then wall thickness will be less. Okay. And length we have considered to be 2 meter. Now, if I consider that the material of the tube is stainless steel, then resistivity of the stainless steel is 70 micro ohm centimeter, and the tube resistance for length of 2 meters, and area. What will be area of wire? cross-sectional area of wire will be outer diameter minus inner diameter square. That will be the area of wire. So area of wire will be pi into 1.36 square minus 1.2 square, where 1.36 is actually coming by in 12 mm. If 2 times we are adding 0.8, half of the thickness from one side, half of thickness from other side, then it becomes the diameter. Okay, so this is my resistance of the wire. Now if I consider power to be 894 and 4480, and I know how much is my resistance, then I square R will give me the value of the required current. So required current is 143 and 321 amperes, and corresponding voltage is 6.22 and 14 volts. Is this one clear? And of course one order issue is there. Before selecting the range of voltage measurement and current measurement, we should first perform this analysis. Is this one clear? Now we have to measure the uncertainty in H. So what will be uncertainty in H? H is nothing but Q is equal to heat flux is equal to H into TW minus TF. So this we are writing as delta T. So whatever the uncertainty in measurement of Q is there and uncertainty in measurement of delta T is there, that will be giving me the uncertainty in measurement of H. Is this one clear? So this will be equation, and from this equation if we calculate, then uncertainty in measurement of H for 5-degree temperature difference between wall and the fluid, it will be 14.2%, and for 15-degree temperature difference it will be 4.83%. Is this one clear? Okay, now what will be the expected outcome? I have told you that if we have turbulent flow situation, fully developed turbulent flow situation, then for majority of the fully developed turbulent flow conditions, which equation is valid? Dittes-Boelter equation is valid. So if this refrigerant also satisfies the Dittes-Boelter equation, then our expected outcome will be Dittes-Boelter equation is Nusselt number is equal to 0.023 into Reynolds number power 0.8 and Prandtl number power 0.4 for the current conditions. So I can say from here the ratio of Nusselt number divided by Prandtl number 0.4. If I plot this as function of Reynolds number, and particularly this is plotted on a log scale. Here also you have power, there also you have power. So if you consider the log of both the quantities, then ultimately both sides, because we have power, so if I consider log of both the quantities, then relationship will be linear. Okay, so that's why if Nusselt number by Prandtl number 0.4 you plot as function of Reynolds number, then this relation will be linear, and all your measured data points should come closer to this straight fitted line. Okay, is this one clear? So it means that now by just repeating the experiment for, or by just performing the experiment for 12 mm diameter pipe, if we are able to establish that this particular equation is satisfied, then I need not to repeat the experiment for 2 mm and 35 mm diameter. What I can do, if I have to define heat transfer coefficient for any turbulent flow situation, I can use the Dittes-Boelter equation. Okay, but in certain scenario, if the data does not follow this equation, then what I need to do? I need to first repeat the experiment to check the correctness of the data, and if we are fully satisfied that all our measurements are correct, then whatever the trend my data is showing, based on that trend I can develop some correlation for Nusselt number, and then I can use that correlation for, I can perform experiment for some another pipe diameter within the given range, and then I can test where if that newly developed relation is satisfying for that scenario or not. Okay, so this is how we can actually perform the experiments. Is this one clear? Now after doing this, here we have to also understand that how to install our thermocouples, or at what locations we need to install thermocouples. So typically we know that from understanding of convection heat transfer, if I consider the x, like distance along the length of the pipe, and temperature, then in the developing region my temperature of wall varies something like this, and after the flow is fully developed, it for constant heat flux condition, it actually varies in a linear manner. And if you talk about the wall temperature, mean fluid temperature varies almost in a linear fashion. Okay, so this is developing region and this is fully developed region. Okay, so typically the expected value of the temperature profile, initially it will be almost linear, and near the end it will be saturating because of the edge effect. Okay, so typically whenever we do theoretically analyze the system, in theory we consider that if we are heating up to this point, it means only temperature will come up to this point and there will not be further dissipation of the heat. But in real scenario, whatever the connectors, joints, insulations, etc. you will be putting, there also there will be certain loss of heat. In which direction? Axial direction. Okay, and along with that, typically if this is my pipe cross section, okay, in theoretical analysis we consider that at each and every point of the pipe I am having the same value of temperature. It means there is no transverse or wall conduction. Okay, transverse wall conduction is actually missing. But in actual physical systems, whenever you will be working, you may find that temperature on the top location is slightly higher in comparison to the temperature on the bottom location. So in this scenario, if there is a temperature difference of 1 degree or 2 degree along the wall of the tube, in the transverse direction there will be some conduction heat transfer. Okay, so all these effects will be causing slight variation in the expected theoretically obtained and the measured temperature profile. So that is the reason, because of the edge effect and the transverse wall conduction, you may experience that temperature profile will be something like this. All are clear with this point? And and of course for fluid temperature, because we are considering that along the different portions of the pipe, the pipe portions are subjected to constant heat flux condition. Okay, these portions are subjected to constant heat flux condition, and moreover the T wall minus TF has to be almost same in order to have the same value of average heat transfer coefficient. So ultimately this tells that the variation of fluid temperature will be linear, and of course putting large number of thermocouples within the tube to measure the fluid temperature is not possible because of two reasons. One reason will be, if you have a heated portion, if you have to insert thermocouple through the heated portion, there will be high chances of leakages or other issues, and the thermocouple may give wrong reading as well because it has to pass through the heater coil. Another issue is, if you put large number of thermocouples into the pipe, then these will be actually creating the disturbances, and the flow will not be staying in the fully developed design. Okay, so that's why for measurement of temperature only inlet and outlet we have put, and in between we can make a good linear approximation of temperature profile. Is this one clear? So this would be the expected or sample temperature profile. Now, so based on this analysis, what we need to do, if you are going to do the experiment, you have to propose or you have to use some data sheet, how you will be recording the data. So you can see the data sheet. We have to record ambient temperature and pressure because all the measurements are associated with the ambient condition. We have to see what are the materials we are using, calibration of the instrument, particularly for uncertainty analysis, observation of unsteady operations or unusual behavior, then inlet exit temperature, tube wall. So all the parameters which we need to estimate, and then what is the calculation we need to do. So these are the calculated result finally to obtain the heat transfer coefficient. So this is how this much detailed sheet you have to prepare before starting the experiment. So you should be very clear whatever measurements you will be taking, what you will be obtaining with these measurements. If this clarity, the clarity on the calculated portion is not there, then it may happen that say you have not recorded the fluid temperature, you have only recorded the wall temperature, and when you have seen the formula, then you will be coming to know that you require fluid temperature also. So then again you have to repeat all the measurement, you have to modify the setup. So that's why all this analysis, whatever output parameters you will be calculating from your primary measurement points, these should also be clear to you. Okay, so all are clear with this point, and these are the further calculated parameters, uncertainties in calculated parameters, and then again finally what we do, we present all the results in the graphical form to interpret the outcome, experimental outcomes, or to develop certain correlations or theories. Is this one clear? So this is all about planning of experiments. From the next lecture onwards, we will start discussion on computational modeling of multiplication.